We will not wait for. Okay, you go live. We'll wait till he comes to start the lecture. At least they should see that I have come. Hello, hello, hello. This is coming right now. Okay. Good afternoon. Uh, we are back at Neutrons at Prof of Condensed Matter. This is the seventh lecture. Uh, I have talked to you about the formalism for calculating neutron scattering cross sections, and at the end of the development of the formalism, two things we got. One, that we have derived the scattering cross section d2 sigma d omega de as a correlation function g of rt, Fourier transform over a correlation function g of rt, and we derive an s of q omega for the system. More importantly, I also showed you and discussed with you that the q omega space is a Fourier transform of a real space correlation function. That means our experiments we are doing in q omega space and the resolution in real space and time are dependent on the range of q. So far as structure is concerned, and range of omega so far as the dynamics is concerned. Today, with this much of introduction, I'll go over to how we make the instruments, not great details, but you should get an idea about the kind of instruments that are available to you. I will mostly be showing you instruments which are available with us at BARC, but by no way they are restrictive. The basic principles are similar. This lecture will mostly focus on work being done or the way it can be done in a reactor source. These are known as continuous sources. So we use, in general, we use monochromatic neutrons. That means we monochromatize a neutron and use them. On the other hand, I will, in the later part of this series or this series of lectures, I'll come to instruments which work at spallation neutron sources, which are actually pulse sources. So there, the neutrons come in pulses of neutrons. Typical frequencies in the range between 50 hertz to even as low as few hertz. And then there we use an alternative form of spectroscopy known as time of flight techniques. So that will come later if time permits. But today I will discuss with you the instruments and their working principles. So I discussed this with you in the last lecture, and I'll emphasize that the length scale, as you go to longer and longer length scale, we need to probe shorter and shorter Q values. That means the angles. And similarly, when you go to faster and faster inelastic processes, we have to go to higher and higher neutron energy transfer. So these axes are counter moving, if I may say. So with this much, this is the reactor hall that I showed you earlier. You have seen it looks pretty crowded, and also I wanted to show you that this is the reactor block. I'll come to in little bit more details, which is a cylindrical block. The actual reactor is much smaller than what you see from the outer perimeter, and there are instruments which receive beams from the neutron. When we say beams, and also there is a neutron guide. All these I'll take a little bit more details and the kind of experiments that you can do using these instruments. So instead of showing you photographs, it makes sense if I show you the schematic of the reactor. This schematic of the reactor is as the following. The plan view, I will point out, this is the core of the reactor. This is where the neutrons are produced in fission. So neutrons are produced in fission there. They come out. Now neutrons being neutral particles, it is difficult to direct them. So I must point out to you that usually neutrons cannot be bent so easily. Not that they cannot be bent at all. They can be, but being neutral, it is difficult to bend them. So a neutron source intensity will generally fall, which is familiar to us, 4 pi r square. That means it follows like a random point source, and that means the reactor core, which I showed you, this core is around 3 meter in diameter, and here these beam lines, this distance is almost 5 meters. So in this 5 meter distance, it goes by if I may take centimeters, so it falls by a factor of approximately 10, 2500. So by a factor of 10 to the power minus 5 to minus 6. So to start with, I have 10 to the power 14 typically neutrons per centimeter square per second. That by the time it has just come out of the reactor here, By the time it has come out, it has fallen by a factor of 10 to the power 5. So actually I have got here at this point 10 to the power 9 neutrons per centimeter square per second. Compare this with the brightness of a bending magnet in a synchrotron. That will be typically in the range of 10 to the power 24 photons per centimeter square per second. We have also per steradian. It's highly focused, and look at this number. This is one disadvantage of neutrons, and whenever we are planning in experiments, we have to always remember this. Now, what comes out here, as I told you, is 10 to the power 9 neutrons per centimeter square per second. It's a Maxwellian. And this Maxwellian, if I want to go ahead and do experiments, so as I showed the day one, this is a Maxwellian like this at the temperature of the reactor, which is typically around 50 degrees centigrade. I would say that is around 330 Kelvin. So the Maxwellian peak is around 330 Kelvin, which is typically around 30 millielectron volts. But this is a polychromatic beam. And as I have been talking all along, I need to have a direction which will dictate my K given by the wavelength of the neutron and energy. So I need a monochromatic energy, I need a direction. So I need a collimator and I need a monochromator to monochromatize. So what we do actually for every experiment, we try to take a slice of this Maxwellian. And when you take a slice, you have to remember this slice will give you a delta lambda, a spread in wavelength. Also, I have to collimate the beam. Collimating the beam means basically using something like a slit in the beam path. So that will also cut down number of neutrons, but it will restrict the direction, and that will give me a delta K. So I will have a delta lambda and the delta K that will dictate the resolution of my instrument, and that resolution and K range both should be commensurate with the studies that we propose to take up in that instrument. So first part, the monochromatization part. So let me go ahead. So how to monochromatize it? That all of us know by Bragg diffraction. So a polychromatic beam comes, and in the beam path, I keep a crystal, a single crystal, which is known as a monochromator. This is also similar to what we do in an X-ray diffractometer. So from the D-spacing of the chosen Bragg plane, I choose a lambda. Moreover, these crystals, if it's a perfect single crystal, then there is again some problem. Problem is as the following. You see the optimization that you have to go logically. You see, I have a Maxwellian. I want to take a slice of it. If I take a perfect single crystal, then that slice will be too narrow. And a narrow slice means very few number of neutrons. I don't want that. So I want a lambda but I also want a spread around the lambda so that I can get reasonable intensity. So that is achieved by what is known as mosaic crystals. Mosaic crystals. Uh, I hope some of you are familiar with the term mosaic crystals. Like most of our electronics materials, they are on silicon wafers. You may be knowing, most of you know, and these silicon are basically silicon, very high quality single crystals. But a mosaic crystal is a crystal which is, as the name suggests, is made of crystals which are slightly misoriented with the crystallites, large enough but misoriented with respect to each other. We can create this misorientation. So the crystallites are slightly misoriented. So we will have the same lambda, but with a larger, but with a spread around this because of the orientation of these crystallites in that direction. So you will get a beam which is not as it is coming from the perfect single crystal, but with a wavelength spread and an angle spread. And that is known as a mosaic crystal outlet. And then I get a, I'm just conceptually, a larger slice and number of neutrons coming to my sample. This is necessary because again and again I am harping that you have only 10 to the power 9 neutrons in my place which has come. Even if you go to a very high power reactor, it will be a similar number, maybe 10 times more, maybe 15 times more, not more than that. Tiny compared to if you go to a synchrotron or even a laboratory access source. So this is what I want to tell you. So this is a monochromator, and what you saw here in this photograph, now it will make sense. You see there are these drum-like objects. These are known as monochromator drums. These are known as monochromator drum. As the name suggests, you can see this cylindrical drum. At the center of it, in the center of this drum, of these drums, there is a monochromator crystal, with some mosaic spread. Typically, it can be copper, it can be germanium, it can be silicon, depending on the wavelength that you want to use it at the angle. So, but why this huge drum? The answer is common sense. In the reactor core, along with the neutrons are produced, the thermal neutrons that are having, there are also lots of very fast neutrons. Fast neutrons are not of much use for us, but harmful to anybody trying to do experiments. And also there are lots and lots of gamma rays. This is coming from the nuclear fission reaction, and they are also contained. So this monochromated drum is there to arrest all of these, because you can see that the experimentalist has to come at these places, at such places, and he should be safe. So we need to arrest all this unwanted radiation before he can start working. So that's why the monochromated drum is used. This is made of neutron and gamma absorbers. And I can tell you, each drum weighs in the range of 14 to 20 tons. It's a huge thing for the safety. So this is located. Moreover, there are these beam lines. Now, once I've explained you how we monochromatize the beam and take it to a more interesting, another interesting point is that we have to think about these beam lines. These beam lines are nothing but, you can say, if I consider the reactor core, the reactor core where the neutrons are there, these beamlines are basically holes in the reactor core, literally holes, typically around 100 millimeter. We have also 300 millimeter diameter beam lines to allow the neutrons to flow out. This is common for all the reactor based sources, that the neutron flows down these holes and reaches out at these points. Now, if you see here, there are certain geometry of these beam lines. You can see if this is the core, there are beam lines which are radial, that means looking at the core. There are beam lines which are tangential, and there are beam lines which are going across the core. All these have very interesting logics. Actually, in a radial beam line, actually, the neutrons inside the core, they undergo these collisions. And every moment they are undergoing collision and their path is changing. But not so for the gamma rays. They actually, once they are born in a fission or in the decay of a fission product, they start moving radially outward. So when that happens, then if I have a beam line which is not looking at the core but at a slight angle, then I can avoid lots of these gamma rays. So a tangential beam line allows me to reduce the gamma background in the reactor. There's a through tube. This through tube is interesting. Here, actually, this through tube is not really through, but there's a small portion where there is some moderator here. Now, that means this through tube doesn't look at the core at all. It is through, and only those neutrons will undergo very large angle collisions can come out of it. So one is the through tube is in a zone of the reactor where the flux is very high, because the reactor flux, if you plot as a function of radial distance, if I consider the center is here, it falls somewhat like this. It's a cosine curve. Actually, it's a Bessel function, but typically of zeroth order, it falls like that for a cylindrical. So this through tube is at a region of the core where the flux is high, but at the same time, by not looking at the core and only allowing those neutrons which undergo a large angle collision to come out through them, so they see thermal neutron flux, high thermal flux, and less gamma rays. So these are the typical design for the beam lines. Another very important thing in today's neutron scattering, I showed you something called when I showed you the plan, I showed you the reactor hall, and I showed you two long lines. These are known as neutron guides. You can use guides to transport neutrons out from the reactor hull, and this is done routinely. If someone of you plan to do experiments, then you go to any neutron source, whether it is a spallation neutron source or it's a reactor-based neutron source, you will encounter these guides. These guide halls are huge, and just to give you a taste of it, I will show you some of these guide halls just for your. You see, this is how a guide hall looks like. It's a huge hall. This is a guide hall. You can see the dimension of this hall with respect to a man. This is 60 to 70 meter long, and through these there are neutron guides which carry the neutrons out. The principle is very simple. I will come to that in a second. So this is actually a guide, it's shown a guide. And what it does actually, how it carries neutrons. You are familiar with uh, optical fibers. We know optical fibers can carry light through total internal reflection. That is common knowledge to everybody. And actually, they are used almost everywhere today, even in your high speed networks, they depend on optical fibers. So neutron guides are the counterpart of optical fibers. Now here let me tell you that like light, why it goes through an optical fiber, because it undergoes total internal reflection, because n is greater than 1 for light for most of the media. And that's why light undergoes total internal reflection when it comes out from denser medium to rarer medium. That means when it tries to come out from the optical fiber. Here, in case of neutrons, the neutron refractive index is less than delta 1. And this delta is of the order of 10 to the power minus 6. So when neutron refractive index, again I am not trying to give you the basics why it is less than 1. In case of both neutrons and X-rays, this refractive index is less than 1. So for a neutron beam, like light beam, you can define refractive index of a medium. And this refractive index is mostly less than 1. Actually, because it is less than 1, light undergoes total internal reflection, neutrons undergo total external reflection. So what happens is something similar to this. So what happens is that in case of neutrons, if this is a surface, a very, very smooth surface, if it comes at a low angle, I'll tell you how low it is. This neutron gets completely reflected. If I draw the reflective intensity for a neutron of wavelength lambda, it goes like this. Pulses. So there is a region which is known as region of total external reflection. So neutron undergoes total external reflection for a wavelength lambda up to some angle known as theta c. If that is the case, then let me tell you, I can make structures like this, I hope my drawing is good enough for you to understand. So I can make structures like this where these faces inside face is coated, I will say, with a good neutron reflecting material. What is that material? I'll tell you. So once I have that, then once a neutron coming out from the reactor, and if I put this guide in front of it, then once it enters this, it gets reflected, it gets again reflected. So exactly like neutron, like optical fiber, the neutron travels down the guide, and here the loss is not 1 by 4 pi square. No. For those neutrons which are getting reflected, it can be as high as 70% or 60%. I myself did a simulation long time back. It was around 60% for our guides. The neutrons are available outside the reactor, and that's a big help. Why? One, you have seen our reactor hall, how crowded it is. So you need to put more instruments. You need to go to a guide hall and without losing neutrons. Another factor is that the reactor, compared to the reactor hall, because only preferable neutrons are taken out from the reactor hall, you have a better signal to noise ratio. When we are doing neutron scattering experiment, this is an important thing because we have detectors which are measuring neutron, but it is also surrounded with lots of neutron absorbing material because this reactor hall, this reactor hall, this has got lots of background. Lots means, I mean, it's not, I don't mean physically harmful, but for counting systems, it can give a background. We are aware from electronics that the signal to noise ratio should be good. So it is better to go out. So we have two guides. So as I told you, that these guides, they take the neutrons out. What is the preferable coating for a guide? Well, this should be something which will have large B coherent. Why? Because when I wrote n equal to 1 minus delta, this delta is actually, it depends on the density of the coherent material, number density of the coherent material in the medium, and the guides which we have got, they're coated with nickel. Ours is natural nickel, but nickel 50 will be preferred because that has got a large B coherent. Basically, this is an example of diffraction similar to what you observe in optics, optical diffraction. So, as I told you, that the diffraction always needs uh, coherence between the waves coming from one to another, one part to another part to cause this diffraction. So it's reasonable to know, understand that this diffraction also depends on B coherent. More will be taught about this, about these refractive index and neutron reflectometry in a later module. But I just want to tell you that this coating is nickel in our case, but nowadays there are things called neutron super mirror. Just very, very briefly, a neutron with a nickel coating, if the critical angle stops here, a super mirror, that this critical angle can be much larger. We can get to much larger angle when we can get good reflection. That means if this is for nickel, so for a super mirror, this angle is much larger. This might actually confuse you a little. These angles are very less. Actually, these are near grazing angles, near grazing. Like, for example, for nickel, this is 6 arc minutes per angstrom. This means that if I use a neutron of 4 angstrom wavelength, this critical angle for nickel is 24 arc minutes, less than a degree. So up to 24 arc minutes, a 4 angstrom neutron will be reflected by nickel surface. And today there are neutron super mirrors. They can have critical angles double of this. So let us say 48, nearly a degree for the same neutrons. So that means here at the entrance, I can, you see, a certain divergence can be accepted by this guide for transportation. This divergence will be more if I can use nickel super mirrors. But in brief, neutron guides are there to take neutrons away from the reactor, but this is preferably for something called cold neutrons. Cold neutrons. This term may be new to you, but cold neutrons means neutrons which are of lower energy. And many reactors, most of the reactors today in the world, advanced reactors, will have cold neutron sources. More about it if I have time later, but now let's go ahead and so this is how the neutron guides. Those they are typically 1 meter long, as I was showing you that rectangular geometry, and these guides you can see they take neutrons out. These guides actually neutrons flow down these guides. These are the guides, and you can see that with guides, with neutron guides, we can accommodate lots of experiments outside the reactor hall where the space is not available. In this case, this guide hall will be typically, it's around 40-meter wide, and the length may be something like 60 meter. This is NIST guide hall. NIST, it is in USA. So this guides help us to set up a lot more experiments. So in brief, the point is that we can take away cold neutrons away from the core, and then away from the neutron reactor hall, and take them to neutron guide halls and set up our experiments over there using this cold neutron as you see here. Now I will discuss with you these experiments that are being made. Again, another guide hall you can see typically. Another important point is that because we always bother about backgrounds in our experiments, if you can bend the guide a little bit, as I'm showing here schematically, uh, the, excuse me, uh, this is these are the guide elements, which are either you can make a straight guide, like this. The typical dimensions are these will be around 1 meter. These will be about 2 centimeters, and the heights typically, so this rectangular cross section, this is can be around 2 centimeters, this can be around 10 centimeters, and these are around typically around 100 centimeters typically length each. So you can arrange them like this, or you can start bending them slightly. So it's just like a bent optical fiber. Only the control over angles have to be more precise, because the whole external reflection is taking place in a very narrow angular range. That is the only difference. In principle, they are very similar. If you can do that, then you can move away from the direct path, and the gamma cannot follow this curvature because neutrons are following it through total external reflection. Gammas cannot follow. So you are not looking at the core of the reactor, and you have got clean neutron beam. Clean neutron beam. So I have given you a very brief summary of how we carry the neutron beams from the reactor to the reactor hall or to the guide halls, and how to go ahead and monochromatize them for the experiment. Now, with this introduction, I will go back to what I was discussing. Well, one more point is that when you look at a bent guide, then the transmission depends on transmission curve looks like this. So another preferable thing, because it rises with lambda like this and goes to a saturation. So lower side, it cuts off the low lambda, low wavelength or high energy neutrons, and allows the low energy neutrons to be transported. This is another schematic. So while you saw those huge monochromated drum covers the face of one beam hole, and another monochromated drum can come only at a distance of typically 2 meters, but you can put in, if you consider a beam hole of 100 millimeter diameter, then you can put number of guides in this 100 millimeter, and then you take them diverging out. They are diverging out, and by the time they reach the guide hole, I was showing you those guides. The difference between them are meters, and you can easily put number of experiments and more number of experiments in on one guide hole. I will show you just now. So you see, this is the guide hall which we have got in Dhruva. So there are two guides. The reactor is in this direction. The neutrons come out. This is guide 1 and this is guide 2. There are two guides, and in this guide there are two gaps, one here, one here. In the first gap, there is a small angle neutron scattering machine. In the end of this guide, there is one more small angle neutron scattering machine. Between the two, there is a polarized neutron reflectometer. So that's a beautiful thing, that you have gaps in a guide and you can put different instruments at these gaps, and on the same guide we have got three instruments working. Why so? Because you see, I have got a Maxwellian, it's low energy part coming out, not the entire Maxwellian, low energy part. So I have got a low energy part of the, if I see the low energy part coming out, it is somewhat like this. Let me just explain. And for these three instruments, possibly I take different wavelengths. So when I take one wavelength out using a monochromator from a beam, for other wavelengths, they can go through the monochromator. Neutrons, unless they are Bragg scattered, the materials are highly transparent to neutrons. This will not happen for X-rays. So the rest of the neutrons, they go through this monochromator, and then I can choose the rest of the monochromator, another wavelength for another instrument, and maybe possibly a integrated wavelength for the third instrument. So on the same beam line, we can put more number of instruments. This is also another advantage of using neutron guides. So we have two guides in Dhruva, curve guides. One has a radius of curvature of 1.9 kilometers, and the other one is approximately 3.5 kilometers. So you can see this is marginally curved, but this marginal curve guide, when it runs over 34 to 40 meters of length, it curves enough to avoid looking directly at the core of the reactor, from where fast neutrons, gamma rays are also accompanying the cold neutrons or the slower neutrons, which we want to take out and use for our experiments. Yes. So if you remember, last time I showed you a curve, showed you a transparency in which I divided the scattering experiments into two parts. One where we do elastic neutron scattering experiments. So that means only structure at various length scales. And other part I showed you inelastic work, where actually I showed you that you have to measure the not only the direction of the outgoing neutron, but also the energy of those neutrons, and they tell us about the dynamics in the system. So today I can sort of this is a walk through the instruments with this divide in mind. So in the first part, I will discuss with you the elastic neutron scattering experiments which we have, and I'll give you briefly, because some of these will be discussed in greater details in later modules, but this is just to give you an idea of what are the instruments that are there available in the country. Such instruments are available all over the world, and sometimes at advanced sources with a higher intensity, but these are accessible to all the Indian neutron scattering community, people who want to do neutron scattering for structure work and dynamics work. With that, let me show you that. So the first part in this walkthrough, we will be talking about elastic neutron scattering experiments, which we have. And the next part, we will talk about the dynamical, the instruments which can take care of the dynamical studies. So I wish actually I could invite all of you to actually physically walk through it. That was the plan when we thought about this course 1 year back. But since then, many things have happened, including the pandemic. And so you have to be happy with this virtual tour. But I hope the concepts and the ideas will be embedded in you, so that in future, when you plan experiments, you can think about a specific instrument. So first part is that a conventional neutron diffraction with Rietveld analysis. This is straight away, you can see that this has come from X-ray diffraction. So with X-ray, we can find out crystal structure, we can find out strain, I discussed with you earlier, we can find out particle size, and we can also find out if there is a preferred orientation. All these we can do with X-rays. Same thing we can do with neutrons, but we can also find out magnetic structures, which is the biggest advantage or biggest attraction for neutrons. So usually it goes like this. You make a sample and you don't immediately run to a neutron diffraction. No. So you make a sample, you do an X-ray diffraction, mostly a powder X-ray diffraction, because most of you will be making powder samples. Making single crystals are difficult, and if you want to study single crystals, you have to have a dedicated program and reason why you want to study single crystals. Otherwise, mostly you will be doing powder diffraction, and then with Rietveld analysis is powder diffraction modification, powder diffraction structure determination in terms of refinement. Refinement means we have a given structure, you will modify to fit the data that you get from your sample. So I am just showing you two instruments here. Here again, this is the reactor block, as you see, and you can see this curved thing. Here also you can see this thing. This is very interesting actually. Before I describe that to you, what is there inside, you see the Q range of these instruments. The one diffractometer we are showing here, you see the Q range is typically 0.4 to 9.4 angstrom inverse. If you remember, I made a comment that when you are doing crystallographic structure, you typically want to a Q max of around 10 angstrom inverse, because you want a resolution in your real space of zero point 0.1 angstrom, which is good enough to find out the crystallographic structure. So these two now justify that you have a range typically like this. And for both these instruments, interestingly, the earlier days, what you used to do, you have a monochromatic beam and the scattered beam goes out. Scattered beam goes out like this. You have a detector moving in a circle. So first, I will put my detector here, count for some time, put my detector here, count for some time, put my detector here, count for some time, and so on and so forth. For step scan, we used to do step scan. And that takes time. Today, there are something called position sensitive detectors inside these radiation shieldings. These are the shieldings for those detectors. So position sensitive detector works somewhat like this. You have the sample, a monochromatic beam, as I told you earlier, falls on it. Now you have a position sensitive detector. It's longish like this, typically around, this may be around 20 millimeters. This is around 1 meter. So now you see why it is called position sensitive detector, because there is a central wire. This works like a typical charged wire principle. You know, at least I'm sure some of you have been introduced to detectors in which you have a central wire, which is an anode, and the body is the cathode, and the charge particle is detected. Interestingly, in this detector, it uses the same principle. So neutron interacts either with boron or with helium. I will not get into these details, and give rise to charged particles in vicinity of this central wire, which is here. And then a charged cloud moves, a negatively charged cloud moves towards the anode and gets collected here. And this detector has the capability of finding out where it has hit. It knows the position. That's why it's called position sensitive detector. So this position sensitive detector can detect the position, and by knowing the distance, simple geometry, you know the angle. So this allows us to collect data at a time over a large angle. And actually not one, but there are 5 detectors sitting here. So you can collect the entire diffraction data at one go. That saves a lot of time, and that allows you to use relatively smaller samples. Sometimes that can also allow you to use in some places something which is happening in situ. So these position sensitive detectors, the position sensitive detectors, or PSDs detectors, they have come in last 20 to 25 years, and they are a big help in getting diffraction data. And powder diffraction data is the most common target for most of the researchers, where especially that's what I told you, that if you have a magnetic sample in which you are interested to know the magnetic structure, then you will be using one of these diffractometers here, as I showed you, using this Q range. And this is just an example, an arbitrary example actually. This is basically, only thing I want to say is that in this Rietveld fitting for the data of this LMNO3. These peaks are fitted by Rydberg technique, and not only you get the position of atoms, but you see with respect to a fractional charge change, fractional change in this LA 1.2 SR 1.8 Mn2 minus RUX with respect to X going from 0 to zero point 0.1, this magnetic structure changes, and you can fit it doing Rydberg fit. In this matter, I want to tell you that I talk about Fourier relationship between the real space structure and the Q space structure. But rarely, as I told, in principle, you should be able to do a Fourier transform and get into the real structure. But you see, your Fourier transform involves an integration over Q 0 to infinity. So that means when I do my experiments, I should have a range going from 0 to infinity. We don't have it. We have got the necessary resolution inherent in the system, but we don't have the range. So rarely we go from SQ omega space, or here SQ, no energy transfer, SQ to G of R, which is basically the structure in real space, through a direct Fourier transform. Rather, what we do in Rydberg refinement, we have a structure to start with. That means I have got a G of R. When I mean this G of R, it takes care of physical structure plus magnetic structure. I generate the S of Q because here there is no restriction of experiment. I generate the S of Q. I may call it theoretical. Let me use the palette. It will be clear. So I have this G of R with me. I know this. I can say model, and I generate the S of Q, which is a model S of Q, and I have the S of Q measured, experimental. And now it is very easy for you to understand. I do a chi-square minimization by playing with the parameters of the model. So I play with the G of R. I keep changing my SM till I get a good chi-square fit. So you can ask that what is the guarantee that I have got the right answer? No guarantee. So what we say that you start with a physically reasonable model and you will get a physically reasonable answer quoted. This physically reasonable is up to you. So many times you might not get a physically reasonable answer. There are examples of that, but in general, mostly you will do and you will get the answer, and that's what gives you this. You can see the data, the fit. These are the misfits at the places, and of course, this is I don't want to get into the discussion because this will it's a room temperature data and the 15K data where the sample is having a magnetic structure. So I think I will keep talking to about the elastic experiments, because the next important thing is that so far, whenever the term diffraction came, we talked about crystallographic structure. But that may not be true all the time. In the next lecture, I will come to you diffraction from liquid and amorphous materials. They're very important. Like liquid and amorphous materials and liquids, they may not have the long range order as you see in a crystallographic material, but they also have short range order. And today I couldn't do that. I'll take it up in the next class, what it means and what we get and what will be the instrument that you will need to understand the short range order in liquids and amorphous materials. Before I stop, two things. Next day, 21st, day after tomorrow, we have the lecture from 11 o'clock in the morning. Please note, 11 o'clock in the morning. This has been scheduled because we have to avoid clash with some other meeting. Please note it. 11 o'clock in the morning, I'll be here. This is one. Secondly, I had given you some assignments. So far, I haven't got back from any one of you. You need to give it to me because people who are desirous of getting credits, they need to give the assignments and also do a project to get the credits. That's it. I will stop here and I will take any questions right now. And I will again repeat that if you want, you can even drop questions at this place. Neutron course at gmail.com. Okay, so I'll wait for some time, hoping that some of them will have come up with some questions. Please. There is some question I can see here. No. Anything? No? Should we wait or should we? Okay. I hope that you have questions and you will drop it. So the Navratri has started. Happy Navratri to all of you. See you day after tomorrow at 11 o'clock. Please note, 11 o'clock in the morning. Bye.